Howdy students, this is 6.3 covering Hess's Law. Hess's Law states that the change in enthalpy from products to reactants, or the delta H, is the same whether the reaction occurs in one step or in several steps. So that means that it only depends on the beginning and the final. We would say that it's pathway independent. So we can take the sum of all of the delta H's, add them together, and get the total reaction. So there are a couple of rules here that we need to cover. The first is if the reaction is reversed, then the sign of delta H must be reversed, and we'll practice this later. If the coefficients in a reaction are multiplied by some sort of whole number integer, then the value of the delta H must also be multiplied by that same number integer. And then you just need to make sure that everything cancels out. That might be something called an intermediate. And then we find our final delta H for the total process, rather than just a specific reaction. So if we're looking at this picture on the right, if we're going from A to D, we can simply say that the delta H is a summation of delta H1 with delta H2 and delta H3. They are equivalent. Here is Hess's law applied to a real-life reaction. On the far right, we have nitrogen gas mixing with oxygen, creating nitrogen dioxide. In a one-step process, we will find that the delta H is 68 kilojoules for this process. Now, if we take a series of two steps to get there, nitrogen plus oxygen yields nitrogen monoxide, and then this intermediately reacts with another set of oxygen to create nitrogen dioxide. Well, in this case, it's a two-step process. The first step would be 180 kilojoules. The second step would be a negative 112 kilojoules. And together, when we add these two, they equate to 68. So these two processes are equivalent, even though the reaction pathway was different. First example, given the following reactions and their respective enthalpy changes, calculate the delta H for the reaction. I actually really love doing Hess's law because it reminds me of a puzzle. Consider this reaction your goal reaction. This is the overall that you want. Consider this in that picture that we saw, point A to point D. And here, they're giving you A to B, B to C, and C to D. That's essentially what we have. Everything must flip or be multiplied or scaled down to match the goal reaction. So if I'm doing this, the first thing I want to do is find the reaction that has carbon. Well, that's this one. But I need two of them. So right away, I'm going to write this reaction out. I have carbon plus oxygen yields CO2. And that value is going to be negative 393.5 kilojoules per mole. But there's a couple things that are going on. I need to have 2 moles of carbon. So I'll show this with a different color. I need to scale up everything in this reaction by 2. And if I do that, then I must scale everything with the delta H by 2. So now my carbons are taken care of. Let's look at the hydrogens. Well, right now, my goal reaction has hydrogen on the left side, and the reaction down here has hydrogen on the left side. So I'm going to go ahead and copy that down. H2 plus 1/2 O2. And that's okay because in this reaction, they're assuming 1 mole of H2, which means we have to use a half coefficient for the oxygen. So it appears that as of right now, I don't need to do anything to this reaction. So let's just copy this number down. Negative 285.9 kilojoules per mole. And then the last step, the goal, so hydrogens are taken care of. The last one, I've got C2H2 on the right side. But I'll notice that I have C2H2 on the left side. So I need to reverse this whole reaction, which means I'll have two CO2s plus H2O yields 5/2 O2 plus C2H2. So let's check in on where we're at as far as balancing goes, because I do have my C2H2 in the right place. Everything else besides the goal reaction must cancel out. So let's check on those oxygens. 2 and 1/2. Well, 2 is just 4/2, so together that makes 5/2, and that cancels with the 5/2 O2 here. The two CO2s cancel, and the H2Os cancel. So I'm left with my goal reaction of 2 C's plus H2 yields C2H2. My goal reaction is satisfied. And I reversed the last reaction, so the negative 1299.6 kilojoules per mole. I'm going to have to reverse the sign or multiply by a negative, which in this case becomes positive 1299.6 kilojoules per mole. Go ahead and pause, add these values together, see if you can find the final answer. Okay, let's reveal the final answer. When we add the two together to get our goal reaction, we get an enthalpy value of 226.7 kilojoules. Second and final example, the heat of combustion of carbon to carbon dioxide is negative 393.5 kilojoules per mole of CO2, whereas that for combustion of CO to CO2 is negative 283.0 kilojoules per mole of CO2. Calculate the heat of combustion of C to CO. So first thing we need to do is write our goal reaction, and it says the combustion of C to CO. Now, to make this happen, I know that combustion requires O2, but that gives me more oxygens than I need. So I am actually going to place a 1/2 coefficient in here, because I'm assuming that they're talking about 1 mole of carbon to 1 mole of CO. Now, our other reactions that are given, and remember we're looking for the delta H here, the other reactions that were given are carbon to carbon dioxide. And that reaction is also combustion, and it's carbon plus oxygen diatomic to yield CO2. Nothing needs to be changed there. But they also give us another reaction, the combustion of carbon monoxide to carbon dioxide. For this one, I need to go ahead and put in oxygen as well, because again, it's a combustion. But in this case, I only needed 1 oxygen to make this happen, so I'm going to throw another 1/2 coefficient. Now, the values of these are given as negative 393.5 kilojoules per mole and negative 283.0 kilojoules per mole. And notice how it says per mole of CO2. So we had to make sure that we had just 1 mole, and we do. We have 1 mole for both of these. If it said something different, then we might have to change our reactions. Now, let's rearrange to find our common goal. And if I'm looking at the carbons, then I notice that I have a carbon on the same side. So I'm just going to copy down this first equation. Carbon plus O2 yields CO2. And then the next thing that I might look at is the carbon monoxide. Sometimes those oxygens we save for last because they're split. They're in 2 different places. Maybe I'll change color for this one. Let's change color. I noticed that in the goal reaction, the COs are on different sides, so I will have to reverse this reaction. So I'm going to flip it. CO2 yields carbon monoxide and 1/2 O2. Okay. Now what I'm going to see is what cancels out. Well, the CO2s cancel out. And then I'm left with a carbon, which is what I wanted. I'm left with a CO. Let's see what's happening with these oxygens. I have a half on this side and a full oxygen on this side. So this will cancel, and I'll be left with 1/2 of an oxygen on this side. So my overall goal of C plus 1/2 O2 yields CO is complete. Now let's look at our values for our numbers. We did not change the first one, negative 393.5 kilojoules per mole, so that stays. And the negative 283.0 kilojoules per mole, we had to reverse that. So I'm going to change the sign and multiply by a negative, which in this case would make it a positive 283.0 kilojoules per mole. So if you want to pause and calculate, let's go ahead and reveal the answer. So in this case, our goal reaction ends up being negative 110.5 kilojoules per mole. This process is exothermic, whereas the first example we did on the last slide was endothermic. Thanks. Y'all have a great day.